Hello, my name is Strider Bona. I'm the president of the Mizzou Space Program here at the University of Missouri Columbia. We are a competition rocketry team here, and we build rockets. Our emphasis tends to be in competitions. We contribute both to the Argonia Cup and the IREC, the new name for the Spaceport America Cup. We do propulsion research, and we do Tripoli certs.
I'm Evan Haefley.
And I'm Ryan Maluski, and we're both project managers for the Argonia Cup this year.
So originally for our design, we went with a 3.9 inch diameter full carbon fiber body tube for the sustainer. This is very similar to our design from last year because we got very close to placing. We had successful staging and ignition, but our recovery did not work. So we went with a very close design that would give us a similar score.
But this year we did some more optimizations on our scoring, and we ended up settling on a full 3-inch, 75 millimeter minimum diameter rocket for both stages. And we're going to be using a almost identical motor setup to last year. And this will get us to roughly 20,000 feet of altitude, carrying around 18 golf balls in our sustainer.
Here's the exploded view of our rocket. So you can see here comes out the sustainer eBay, which is going to contain a GoPro, a tele-GPS, and a radio transmitter for recovery efforts. And then there are the 18 golf balls that lie in the nose cone and forward sustainer. And then there's a Cesaroni 2-grain 75mm motor casing, which will act as our interstage coupler. And both of our motor casings are connected to 4mm carbon fiber thrust transfer bulkheads.
So for our sustainer, we are using our Cesaroni 2-grain casing as our interstage coupler. So this will be hanging 6.5 inches out the back of our sustainer. This is what we did last year. We did have successful staging and ignition. So we're doing this again just to try to replicate that success.
Hi, I'm Cooper. I'm a member of the Mizzou Space Program, and I led our Argonia project last year. We're using the same motors this year, starting with a K1800 in the booster that has 2,444 Newton seconds of impulse, and then staging in the sustainer to an L585, which has 2,653 Newton seconds of impulse. And added together, they come in just under the allowable limit. And we chose the K1800 because it's a very fast burn motor that gets us off the pad, and then we immediately separate the booster. And then after the optimal delay, which is around 8 seconds, it looks like, we'll ignite the sustainer motor, which is a slower burning, very efficient motor. It's the most impulse that we can fit in this case.
I'm Drew. I'm a team member, and I'll be talking about our recovery system. This year, we've decided to go with the classic dual deploy system because last year we tried to use a tender descender, but for unknown reasons, it didn't deploy properly and it didn't work. Our booster will have a descent velocity of 30.72 seconds. Our sustainer's drogue chute will have a descent velocity of 70 feet per second, and our sustainer's main chute will have a descent velocity of 23 feet per second. It will hit the ground at 24 feet per second. If for some reason the sustainer doesn't light, then its drogue chute will have a descent rate of 78 feet per second, and its main chute will have a descent rate of 28 feet per second. Our booster chute will be a 3-foot Rocket Man. Our sustainer chute will be a 36-inch Fruity chute, and our sustainer's drogue will be a 2-foot Rocket Man. For all our shock cord, we'll be using 3/8 Kevlar with 3 built-in loops.
For our booster avionics, we have a Blue Raven as the primary flight computer and a Raven 4 as backup. And those control primary and redundant separation charges on top and primary and redundant parachute deployment charges on the bottom. And the way this works, this is ours from last year. We don't use a coupler, and the airframe is all one solid piece. The avionics bay shoots itself out and is attached with shear pins to start. And that way we save a bit of mass and volume. But we made some upgrades this year because this one allowed a lot of the gases to get in. So the flight computers got a little dirty, but we're gonna fix that this year and refly it. And we also have a falconry tracker for the booster tracking.
For our sustainer avionics, we will have a featherweight Blue Raven as our main flight computer and an Ultra Spectrum Easy Mini as our backup. Our avionics bay will also contain a tele-GPS unit that will make recovery much easier, as during heavy winds and with a 20-degree tilt, our sustainer could drift as far as 3 miles. So that'll be really nice to have. And we'll also have a camera in there as well to record footage. Our sustainer ignition should happen around 5,000 feet at 370 feet per second. So to make sure that we're on course, we're going to have a lockout where the sustainer motor will only light if we're traveling faster than 250 feet per second, at less than 20 degree tilt, and greater than 4,000 feet in altitude. For our sustainer ignition motor, we will have copper wire running down the length of our motor casing from the inside the motor to our avionics bay. It's what we used last year, and it worked really well. And then connected to that copper tape will be an E-match wrapped in ProCast by QuickBurn, which will help with ignition of the motor.
So this is some CFD, computational fluid dynamics, that we did for our rocket this year. So you can see here, like, this is the flow of the velocity over the rocket. And so all these simulations were just done within SolidWorks 2024 using their FlowSim program. And so you can see here the greatest velocity exists at like the along like the just behind the nose cone, and the lower velocities are at the leading edge of the nose cone, and then also in the areas like over the fins as well. And so you can see how the air slows down when it's passing over the fins. And then also you can see like our launch lugs here, how they're not very aerodynamic, so that's why both of them are placed on the booster section. And then you can see here, this is the pressure plot. And so all the meshing was done within SolidWorks. A large scale mesh refinement was kind of outside the scope of this project, but a more accurate result could have been found if we were to use a program such as ANSYS and refined our mesh for of the model. But this is a well enough model because this was just used to verify our fin flutter and velocity results. So yeah, you can see how like the areas of greatest pressure exist at like the nose cone and the leading edges, and then the lowest pressure are from your Mach waves and from the area like your trailing areas as well.